more numbers. If we keep going, there'll be another. Somewhere down the track, there'll be another number. Who's left? You, and you, and you. Okay. Okay. So they're the four people who think there will be another square number. Is there anyone else left in the competition other than that? No. Okay. So it turns out you're all wrong. 4,900 is a special number, so if it ever comes up in conversation there, you can say that 4,900 is special. It comes up here, and after 4,900, amazingly, there's no other square numbers. Well, that's a lot of fun. Here's the question that you're probably thinking, what's this got to do with JPEG? What the talk is about JPEG. And the answer is it's got nothing to do with JPEG. Absolutely nothing to do with JPEG. Okay, so you say, okay, fine. Here's the second question. This is the most common question I get. How is this useful? How are these odd numbers, these square numbers, this 4,900, how is it useful? It's not useful for JPEG. Well, in fact, it's not useful for anything. Totally useless. Outside the world of mathematics, totally useless. So, it's of no use in the real world. As far as I know, I've been involved in maths. I've spent a couple of decades amongst square numbers and number theory, and I'm not aware of any use for anything that I've said so far. That doesn't mean that there isn't a use. Maybe there'll be a use down the track, but on what I know, it's completely useless. But the point is, it'd be wrong to think that all of the maths that we learn about at high school, square numbers and things like that, is useless. In fact, a lot of it's very useful, and a lot of it is actually an essential part of a lot of the really important things that go on in everyday life. So that's what I want to do today. I want to talk about JPEG, and we'll just use basic high school maths. And one of the benefits of high school maths is, other than it's an essential part of JPEG, as we'll see, is that it actually gives us a way to understand JPEG, to really get to the core of how it works. So a little bit of maths is going to help us. So JPEG stands for Joint Photographic Expert Group, and it's a convention for storing and transmitting photos. And in fact, it's the most common way of storing and transmitting photos on the World Wide Web, according to Wikipedia. So here's some photos. Today I'm going to talk about black and white photos, but everything I say applies to colour as well. But I'm just going to use black and white photos. I have here Australian kookaburras, because sometimes this slide's used overseas and I like to sort of promote Australia in a subtle way. A lot of people overseas don't realise that we've actually got some animals that aren't super scary and dangerous. But anyway. So here's our photo, and I'd like you to have a think about how you would go about trying to store and transmit this photo. How would you store and transmit the photo? You've got the photo, you've got a scanner, and you've got your computer. How would you do this? And this is the way most people start to think about how you would do this, how you would store and transmit the photo. You take, this is a part of the photo, but I've blown it up. So you put a grid over the top of the photo, and then you come up with some sort of brightness convention. So today I'm going to use 00 is totally white, 99 is totally black, and you can see there I put an example which I estimated at 45 for this medium grey. And then the scanner goes through and it measures the brightness of each little square, and so it allocates a number to each square. And once you do that, of course, you can get rid of the photo, get rid of the grid, and you've just got the numbers. And if I have this in my computer and I want to send you the photo, I can just send these numbers, and your computer can do everything in reverse. Looks at the numbers, looks at the brightness convention, creates all these little squares according to the brightness, and puts the photo up on your computer. And providing you've got tiny little squares and you've got enough of them, you come up with a pretty good photo. So that's how you start out thinking about storing and transmitting photos. So what does JPEG do? Well, instead of storing all the photos on the left, the numbers on the left, it just uses a few numbers that I've put up on the right. And because you've got less numbers to store, it means that it takes less storage space, it's quicker to transmit and retrieve the photo. So here's an example off Wikipedia of two photos. One's using JPEG and one isn't. And the one with JPEG takes about an eighth of the storage, so roughly about 8 times faster to transmit and receive. So that's basically how JPEG does it. There are less numbers. Essentially, it just uses less numbers. So now the question is, the obvious question is, how does JPEG do that? How can you represent all of this just using this? Now, warning. I'm going to put up a scary formula now. And there's a bit of a saying when you in science communication that every time you put up a formula, you lose about half your audience. And this is a really scary formula. But I'm only going to use one little part of the formula. So I'm going to put it up. Calm yourself. There's no need to turn off yet. Here's the formula. Whoa. But I'm only interested in this, COS. And when you see the letter COS, is what you probably, well, what you might be thinking is, surely this is not cosine from trigonometry at high school. Because, why? Because cosine is about angles and distances. It's about this sort of problem. Here's a flagpole. It's 25 metres to the top of the flagpole, 30-degree angle. What's this distance to the base of the flagpole? Sorry, some of you are probably starting to shake now because a lot of people really didn't like trigonometry. Anyway, so you're probably thinking, this is not cosine. Well, it turns out that it is. So where we've sort of got to is that cosine's not just about distances and angles, which is taught at school. It's actually an essential part of JPEG and other things. And without cosine, there's no JPEG. Okay, so that's good. So, amazingly, in about 10 minutes, I can explain how cosine is used for JPEG. So, here's a simplified example. Instead of looking at the whole photo, I'm just going to take a tiny little line segment, and imagine that it's divided up into 12 little squares. And when the scanner does its job, we get these 12 numbers. So these 12 numbers represent that little line segment. And you can see actually, starts out 72, it sort of gets lighter and then it gets darker. That's whatever, it varies. So the first thing I'm going to do is I'm going to just graph those numbers. So you can see the 72 on the left and the 89 on the right. So far, nothing too difficult. And now what I'm going to do is work out the average. So this seems like a trivial primary school thing to work out the average. But actually we can learn a lot about JPEG just from this average. Because the big step with JPEG is to say to the computer, instead of storing the 12 numbers, we're going to store some other numbers. And the first number that we're going to store is the average. So the computer is not going to store these 12 numbers. The first thing it's going to store is the average, 74. And already we can sort of see where this is heading a little bit. Let's just imagine I stopped now. So the only thing the computer's got is 74. One thing I can say is it'll be a very quick and efficient photo, because instead of 12 numbers, I've only got one number. It's going to be super quick, it'll take very little storage, it'll be super quick to transmit and retrieve, but it's going to be a lousy photo. Because the whole line segment is going to be 74 straight across. It's just going to be a dark grey right across. It's going to be a lousy photo, but it's going to be very quick. So we need to now introduce cosine. So cosine at one level is just like a factory. You shove in a number and it spits out a number at the other end. So in this case, I've put in 2.5 and it's spat out negative 0.8. We don't really need to worry about that. The main thing to notice is about cosine, the red line, the red curve, is that it's just a nice gentle wave or curve that just goes up and down between -1 and 1. That's the cosine curve. So if you tell a computer the cosine curve, it knows that is the curve. And what you can easily do is multiply that by 3. So what I've got here is just 3 times cosine x. So now I'm going to put this on the graph that we had before. So this is a little bit busy. Up the top, I've got the photographic data in black and blue. I've got the average there, and down the bottom I've put this 3 cos x. And you can see it's a lot flatter because of the scaling, but you can see that it is just a nice gentle wave that goes up and down between -3 and 3. And the 3, I'll talk about where I got the 3 from in a bit later, but at this stage I've just, in my wisdom, decided to use 3 rather than any other number. The 3 is the second number that I'm going to tell the computer. So the computer knows the first number is 74 and the second number is 3. And using those two numbers, it will create the graph, or the curve, 74 plus 3 cos x. And that's the curve there. And you can see we've done very little. We've achieved very little. The curve is nowhere near close to the photographic data. In fact, arguably, I've made it worse. So we're going to have to take one more step, at least one more step. So here's the cosine curve. Now it's in black because I want to create a new curve with red. And there's two ways to think about it. The first is you can see that the red curve is just shifted across. I've just shifted the cosine curve across. So you could think of it as the shifted cosine curve. Okay, it's just shifted across by a certain amount. For some of you will recognise that it's the curve of sine x. So cosine, you remember from school, always had a little brother or sister called sine. And so this is the... And this time I've decided to multiply it by -10. So you can see here, -10 by the shifted cos x function, or -10 by sine x. Down the bottom, and up the top is what we got to before, 74 and the 3 that the computer stored. So now I'm going to add it on. And now you can see the genius of JK. The curve that I've drawn with only 3 numbers is very, very close to the photographic data. Now there's a little bit of an issue at the ends here. It's not that good, but we can solve that in another way, which I won't go into. But you can see that for the rest, it's a really good approximation. So the curve is basically as good as the photographic data. It's so good that in fact your eye wouldn't be able to tell the difference. So if you didn't follow all those charts, I gather most of you do, just so I can sort of sense that most of you follow what's going on. But really, what are we saying here? We started out on this line segment recording 12 two-digit numbers, and what I'm saying is that now the computer knows that the first thing is the average, the second is multiply by cos x, and the third you multiply by sine x. So if I now send those, say I want to send to my wife, that line segment, I can just send the 3 numbers, 74, 3 and -10, and her computer will create this curve because it knows that the first thing is the average, the second thing you multiply by cos x, and the third thing you multiply by sine x, and it will draw that curve, and using that curve, it'll just read off the numbers for the photographic data, and it will create a line segment. Here's the numbers, and we saw from the curve, the thing I had up before, that that's going to be a very nice line segment. It's going to be very, very close to the photo. So instead of 12 two-digit numbers, we only need 3. So 75% less storage space and about 4 times faster. Right, that's basically the core idea behind JPEG. You don't need to represent data using photographic data using all the little dots. You can actually just do it with curves. So at this point, I will, if people want to ask questions when I'm finished, I'm happy to take questions, but there are 3 things that people often will ask. The first is, what do you do if the curve doesn't get close enough to the photographic data? I was sort of lucky in a way that after just doing cosine and sine, I got close enough. And the answer is that you just add more terms. So there's a proper mathematical logic to, after using cosine and sine, then use cosine 2x, sine 2x, cosine 3x, sine 3x. This cosine 2x is just a wave. It's basically just a wave like cosine, except that it goes up and down more frequently, that's all. So that's the answer there. You just add more terms. And then there's the obvious question, where do you get the numbers? Where did I get the numbers 74, 3 and negative 10? So the 74 is easy, that's just the average. So the question is, where did I get the 3 and the negative 10? And the answer is that there's a mathematical process or mathematical formulas that you use to get the 3 and the negative 10. It's called, broadly speaking, it's called Fourier series. Now, in my case, I was just lazy. I could work it out myself, but I just got onto the net. Now, if you search Greg Thatcher Fourier, Greg Thatcher has got a program there that you can use, and you just put in any data, and then you can play around with curves. You can say, what happens if I add 5 curves, 2 curves, just the sine curves, not the cosine curves, whatever you want. And it's really fun if you're interested. It's worth having a go at. So that's what you do there. If you're interested in sort of starting to understand the mathematics of Fourier series, I do have a YouTube video, Fourier series made easy. If you understand integration and that sort of stuff, if you're comfortable with that, you'll get something out of that in terms of how Fourier series works. So that's good. So Fourier was a mathematician of a couple of hundred years ago. Sometimes, I think it's pronounced probably Fourier, but it's anglicised now often to Fourier. I'm actually I'm sort of related to it in a way. When I did my PhD, I had a supervisor, and he had a supervisor, and he did his PhD. And if you go back 9 generations, you get to a guy called Lagrange, who was a very famous mathematician, and he had a number of PhD students, of which one was Monsieur Fourier. So, yeah. Enough said. Why cos x? What's so special about cos x? Like, why don't I, instead of using cos x, sin x, cos 2x, sin 2x, why don't I just use, I don't know, x squared, x cubed, x to the 4th? And the answer is that the first thing is that the cosine curves work for virtually any sort of photo. And that's important. It has to work for landscape, for portraits, for shots of the snow, for night shots. So it's important. I sort of glossed over this before because I said you just use more and more terms. Remember, I said you use cosine 2x, sine 2x, cosine 3x, etc. But what I didn't say was that doesn't actually ensure that you'll get close enough to the photo. You could see a situation where you've taken millions of curves and you're still not getting close. And mathematicians have proved that with cosine and sine, you will ultimately get close to the photo. And it works for virtually any curve or any photo. And the second thing is that it doesn't take that many cosine curves to describe the data. This is obviously critical. It's not good enough to get close to the data, you have to get close to it quickly. And cosine and sine, for reasons we don't really want to go into here, are very, very special functions. They're very, not only do they work for any photo, but they're sort of very, very efficient, incredibly efficient. So by working out the best thing for cosine x and sine x that I did, nothing's wasted. And so when I come to cos 2x and sine 2x and those other curves, I'm not duplicating what I did with the cosine and sine. It's very efficient. These are just for reasons, mathematical reasons, which I won't go into, that they're just incredibly efficient curves. And really sort of fairly unique compared to all the other curves that you can come up with. So just to finish up before I take some questions, if you want to see this talk again because you're confused, you can have a look at my YouTube video on how JPEG works. If you put that in, it's number 1 or 2 on YouTube, so you'll be able to find it. I've got some other YouTube videos. If you like the mathematical stuff with the odds and evens and square numbers, I've got a playlist, favourite mathematical stories. And if you're interested in this sort of how other things work, I've got a playlist on that. I've got GPS, Google search, and internet encryption as well as JPEG. And if you prefer live stuff, I'm doing a couple of live things on CT scans and encryption in the next couple of months, so you can have a look on my website if you're interested in that. Apart from that, after that little plug, I'll stop, and if anyone's got any questions, I'm happy to try and answer them. And if I can't answer them, Renee will handle them in the next talk.
Yeah, how does it work for color photos, RGB?
Well, I think broadly speaking, you can allocate a colour, a number to each colour, and so once you've got them in numbers, then it works in a similar sort of way. So providing you can actually think of a rainbow or an array of colours, if you can number them in any sort of semi-sensible way, once you've got the numbers, then there's no problem.
So it'd be a second number, so you have like a shade going from 0 to 99, right?
I think what happens is the more likely you actually have a number for each individual sort of colour up to the amount that you want. But look, I would imagine there may be someone here who actually knows the answer to that more fully than me.
You'll have 3 images, you have to do the image each thing, and it just do the same thing for the next thing. Right.
So you go to Chroma and it's 5, and then you're all sorts of
Yeah.
What does JPEG have different from GIF and bitmap?
Okay. Once again, this is not really my area of expertise because I'm a mathematician, I'm not a JPEG expert. But things like PNG and GIF, as I understand it, work completely differently. This is called lossy compression. Lossy meaning you can lose, because you do actually give something up. Remember how we saw that I didn't get the curve exactly. So the photo is not actually totally accurate, but it's accurate enough for our eyes. And you can particularly get in problems if you keep doing it repeatedly.
I think bitmap would point every little point, I would say.
Yeah, so what they do, what the other systems work, which are lossless compression, rather than lossy compression, they're called lossless compression. They use sort of clever ways to store the exact data. So for example, this screen here, it's one colour. So rather than actually writing out the number thousands of times, it just says for this row across to here, it's all the same colour. So you could see that you can summarise this screen, the back of this screen, all with just 1 or 2 numbers really. You just say it's this colour and it applies to everything. And then you start putting on this black line. Once again, you don't have to actually put every little dot. You can come up with clever ways.
Pixels?
Yeah, but you can come up with clever ways to sort of to record the pixels rather than actually recording each one individually. And there's some clever ways they do that to do that. So a lot of those GIF and PNG work on that system.